Hello everyone, I welcome you all to this lecture. In this lecture, we are going to discuss disk, or we also know disk as hard disk or secondary storage devices. So let's first discuss the structure of the disk and then we will solve few problems on that. So if you look at the disk, the structure looks as it is depicted in this diagram. There are different platters. These platters are divided into different tracks, sectors, and the combination of sectors you can say clusters. So tracks and sectors are there on every platter, and generally these platters stores data on both the sides. So this side as well as lower side of this also the data can be stored. Now these platters are connected to this spindle which can rotate all these platters all together. So they can rotate, and for reading writing there are some assembly or devices which we consider as read-write head, and all these read-write heads are connected with an ARM assembly. Okay, so this ARM assembly can back and forth move. So once we try to move these read-write head, all the read-write head will move along. So that you need to remember. Separately we cannot move, like only this head we cannot move. If we want to move, all the read-write heads will move at a time, right? So the important thing here is you need to remember these platters are divided into number of tracks. The number of tracks, like this is one of the track, the complete circle, this is a track, and these tracks are divided into number of sectors. So like this is one of the sector on this track, there's another sector on this track, so there are multiple sectors on the track. So when we multiply or add the capacity of all the sectors on a track, we can find out the capacity of a sector. Okay, so let's move on and discuss few important terms like tracks. So track is a circular ring on one side of the disk. Each track has a unique number, so each track is numbered. Sector, it is a wedge shaped piece of a disk. Each sector is also numbered. So I have also reflected how the sectors are looking like yellow colored sectors. So these are sectors. Okay, then read write head, it is a device or assembly which can read or write data to a magnetic disk. Then access arm or moving arm, this is a mechanical arm that moves the read or write head across the surface of the disk. It is directed by the OS. So OS will generate the signal how to move the read write heads, and accordingly the assembly will behave. Then platter, it is a magnetic disk where one or both sides of the platters are magnetized, allowing data to be stored. So these platter, generally nowadays we use both side magnetized platter, so both side data can be stored. Now the number of cylinders, so number of cylinders actually reflected by number of tracks. So if you look at here, this is looking like a cylinder, so here it is written like cylinder C. So a particular track, once the read write head will be fixed on a track, so the same track will lower side, then the another disk. So there are multiple tracks we are accessing at a time, and all these tracks when we look in a single go, it look like a cylinder, right? So this we consider as a cylinder. Cylinders, number of cylinders are nothing. If you replace this read write head, let's say on another track, another track, another track. So whatever the number of tracks are there on these platters, that will define the number of cylinders. So the number of cylinders is equal to number of tracks in a surface. Single track capacity. The single track capacity is dependent on the number of sectors per track and the sector size. The number of bytes per sector, right? So when this will be multiplied with total number of sectors per track, then the sector capacity can be calculated. Cylinder capacity. The cylinder capacity is dependent on the number of surfaces and then the track capacity. So on one surface there is a track, it is capable to store some data. Then on another surface there is a track capable to store some data, capable to store. So if there are n number of surfaces, n number of tracks. So we multiply the number of surfaces with track capacity. So that will give us the cylinder capacity. Then disk capacity, the number of cylinders multiplied by cylinder capacity. So the total disk capacity, you can say how many cylinders are there and what is the capacity of cylinder. So in short, you can say if we want to find out the disk capacity, it is number of tracks, the total number of tracks on each and every platter multiplied by sectors per track, how many sectors are there per track, and what is the size of sector in terms of byte. So bytes per sector. When we multiply all these things, we can conclude the disk capacity. Now there are certain times allocated assigned to a disk. The time taken to access a particular block of data consists of seek time. So on a particular block, when we want to relocate and position our read write head, there is a delay or time delay that is considered as the seek time. Then what is the rotational delay or rotational latency? The rotation time is, let's say a read write head is at one particular position, but the sector is away from there. So once the disk will rotate, the sector will come to that. So that is rotational delay. Data transfer, once your read write head on the desired sector, then it will start reading the sector and fetch the data. So the access time, total access time will consist of these three: seek time plus rotational delay plus data transfer. There may be some overhead also, but primarily these three we need to add in order to find out the total access time of a particular block of data. Each rotation of disk covers one track. So if a disk is rotating like one revolution, one track will be covered in one rotation. The data transfer rate depends on RPM. So because the read write head will rotating, like read write head is fixed and disk is rotating like this. So how much data can be read, it depends upon the how fast the disk is rotating. Okay, because the reading and writing is dependent on that rotation speed. All right. Then seek time. So what is seek time? I have already told you. The time taken to move read write head to the desired track. Rotational latency, the time to move read or write head to the desired sector beginning. Rotational latency is half of the rotation time. So you can remember this fact. Rotational latency is half of the rotation time. Then the data transfer rate of the disk is equal to number of bytes per second. So this is the unit, how many bytes per second are being transferred. That depicts the data transfer rate of the disk. Then the disk access time, as I already told you, the disk access time includes the disk seek time, then the rotational latency and the data transfer time, and if there is any control overhead, because OS generate the signal to move the arm and there are other things also. So there may be some control overhead. So by adding all these things, we can find out the disk access time. So I hope by all these things, you must be very clear about the structure of the disk, okay, and how we can calculate different time related to the disk. Now let's try to solve few problems. So you consider one question here given. Consider a disk with the following specifications. There are 16 surfaces. The number of surfaces are 16. 128 tracks per surface. So that means every surface is having 128 tracks. And on every track, there are 256 sectors per track. And every sector is having 512 bytes capacity. Okay. So 512 bytes per sector. That means these many bytes are there in a sector. Now we need to solve the following questions. So the very first question is, what is the capacity of the disk? So if we want to calculate the capacity of the disk, how we can calculate the capacity? It is very easy. In the capacity, we already know that if you want to calculate the capacity of the disk, you need to find out how many surfaces are there, then how many tracks per surface are there, and on the tracks, how many sectors are there, and the capacity of the sector. You need to multiply all these things, and then the disk capacity can be calculated. So if we want to calculate a part, the disk capacity, so let's calculate a part, that is the disk capacity. So the disk capacity can be calculated as number of total surfaces, number of total surfaces multiplied by number of tracks per surface, number of tracks per surface multiplied by number of sectors per track, number of sectors per track multiplied by number of bytes per sector, number of bytes per sector. Okay, so all this data is already given. If you look at, there are 16 surfaces. So if you want to calculate the disk capacity, the number of surfaces are 16. The next is number of tracks per surface. So number of tracks, 128 tracks per surface is given, 128 tracks per second. Then the next thing is number of sectors per track. It is also given, 256 sector per track. So then multiply 256. And then number of bytes per sector, that means sector capacity. So the 512 bytes per sector is given. So 512. Now it is 2 to the power 4, it is 2 to the power 7, it is 2 to the power 8, it is 2 to the power 9. So ultimately it is 9, 8, 17, 7, 24, it is 2 to the power 28. 2 to the power 28, if you want to convert it, 2 to the power 20 is MB. So if I write 2 to the power 8 into 2 to the power 20, 2 to the power 8 is equal to 256, and 2 to the power 20 means mega. If everything is given in bytes, you look at, then it is megabytes. Okay, so this is the capacity of the disk which is given in this question. Now let's look at the next one. The next is, what is the number of bits required to address the sector? So in order to find out the number of bits to allocate the number to each and every sector, we need to find out the total number of sectors. Okay, then we convert the total number of sectors into to the power, and we can take the log base 2, and whatever the value will come, we can say these many bits are required to represent it. So let's look at the B part. So in the B part of this question, we need to find out the total number of sectors first. Calculate total number of sectors. The total number of sectors will be, because sectors are on track and there are n number of tracks on a surface and there are n number of surfaces. So let's say there are 16 surfaces, and on every surface there are, let's say, 128 tracks. On 128 tracks there are certain number of sectors. So how we can calculate the total number of sectors? Number of surfaces we need to multiply with number of tracks per surface. Number of tracks per surface, and this thing we need to multiply the number of sectors per track. Number of sectors per track. Now we can easily find out it. Number of surfaces are given 16. Number of tracks are given as 128, and number of sectors are given 256, right? So number of surfaces 16, number of tracks 128, and number of sectors per track is 256, right? So if you multiply this, it is 2 to the power 4, 2 to the power 7, and 2 to the power 8. So it is 2 to the power 19. If you take the log base 2 of it, so the number of bits required, number of bits required to address each and every sector, to address sector, is equal to, you need to take the log of this 2 to the power 19. That means we will get 19 bits. Okay, so 19 bits are required to number each and every sector uniquely, right? Now let's look at the C part. In C part, they are asking if the format overhead is 32 bytes per sector. Format overhead you can consider as, once we format a disk, we create some additional information from management point of view. It contains some data. So when we format a disk, in a sector some extra information need to be stored, and that is taking, let's say, 64 bytes per sector. That is format overhead. How much amount of memory is lost due to formatting? Because once we format a disk, we can utilize somehow less amount of memory as compared to the total capacity of the disk because of this overhead. So this third question is asking how much overhead is there. Okay, so what is the formatted disk space which we can utilize, and next it is calculating the lost part of the memory. So let's calculate the C. So if we want to calculate C, in C we are interested in calculating the formatted disk space, right? So formatted disk space, if you want to calculate, the formatting overhead is given per sector. So we need to find out how many total number of sectors are there. So total number of sectors, multiplied by overhead per sector, which we are having, overhead per sector. So the total number of sectors are already given. We have calculated total number of sector because we have calculated the bits required for a sector. So bits required to represent a sector to 19. That means total number of sectors are 2 to the power 19. And the overhead per sector is 32 bytes. Right? So when you calculate this thing, it is 2 to the power 19 into 2 to the power 5 bytes. That means 2 to the power 24 bytes. 2 to the power 24 bytes. That means 2 to the power 20, 2 to the power 4 into 2 to the power 20 bytes. 2 to the power 20 means mega and 2 to the power 4 means 16. So 16 megabyte is we consider as the overhead, some extra space which is being consumed inside each and every sector. So if it is 16 MB, then the formatted disk space will be the total space minus this MB. So the total space we have already calculated. What is the total space? It is 256 MB is the disk capacity. So formatted disk space is equal to total disk space we need to subtract the formatting overhead. So total is 256 MB minus 16 MB is the overhead, formatting overhead. So the disk space can be calculated like 240 MB. So this much of disk can be utilized because this 16 MB is the formatting overhead. So this cannot be utilized by the user. Now let's look at the D part. So what is D? D is if the formatted overhead is 64 byte per sector. Okay. How much amount of memory is lost due to formatting? So this is easy. Number of tracks multiplied by the overhead. So it's not a very difficult thing. 2 to the power 19 multiplied by 64 and you will get this answer. So D is easy. Now let's solve the D part. D part, we need to calculate the formatting overhead. So formatting overhead is total number of sectors and overhead per sector. Total number of sectors are 2 to the power 19 and overhead per sector is 64 byte it is given, right? So you can convert it. 2 to the power 19 into 2 to the power 64 means 6 byte. It is 2 to the power 25 bytes. 2 to the power 25 means 32 MB. Okay, 32 MB. So that means 32 MB is the overhead in this situation. This space 32 MB cannot be utilized by the user. Rest of the space can be utilized. Now let's look at the E part. If the diameter of innermost track is 21 centimeter. Innermost track means, like if you look at here, the innermost track is this track, let's say, which is innermost. So they are talking about the diameter of innermost track. So the diameter of innermost track is given as 21 centimeter. That means radius is 21 divided by 2. What is the maximum recording density? Recording density we need to calculate per centimeter. Okay, so let's look at the E part. So maximum recording density we need to calculate in this. Maximum recording density will come in the innermost track, because innermost is having very less diameter as compared to the outermost. So if we are intended to calculate maximum recording density, we should consider the innermost track. So how do we calculate the this particular density? The maximum recording density is dependent upon how much data is getting stored on a track and what is the length of the track in terms of perimeter or circumference. So the storage capacity of a track, we know that storage capacity of a track, and we calculate the total circumference of the track. So because it is a circle, it will be 2 pi r. 2 and r will give you the diameter. So the storage capacity of a track divided by pi into d means diameter, because diameter is already given. Diameter is given as I guess 21 centimeter, right? So pi, we can write 22 divided by 7 or 3.14, whatever you want to write. So let me write it pi as and d is the diameter. So diameter is given 21 centimeter. 21 centimeter is the diameter. Now storage capacity of a track. So the track is having 256 sector, and all the sectors are of 512 bytes. So 256 sectors, and every sector is of 512 bytes. So this is the capacity of one track. Okay, whether it is inner track or outer track, all the tracks are having same capacity, and that track is having this circumference. So you just cancel out this thing, you will get 256 multiplied by 512 bytes divided by 22 into 3. It is centimeter. So it will come like bytes per centimeter. The density will come like that. Okay, so if you solve this, you can divide it, and you can try to solve this. Then somewhere around 2 you will get, or 1.9 something you will get, 1.95 around you will get in terms of kilobytes per centimeter. So the density will come like kilobytes per centimeter. That means each centimeter these many kilobytes are getting stored, and this is the recording density. recording density or data storage density. Now let's look at the next part, that is F part. F part is the diameter of innermost track is 21 centimeter. If diameter is 21 centimeter with 2 kb per centimeter. Okay. What is the capacity of the track? So if per centimeter 2 kb is getting stored, then you need to find out the 2 pi r. So pi will give you 22 divided by 7 and 2 into r will give you d, and this d is already given you. So the diameter is given as here 21 centimeter. So this is like 66 and so this is 66 centimeter actually, and each centimeter 2 kb is getting stored. So you need to multiply 2 kb divided by centimeter. So this centimeter will be cancelled out. That means it will give you 132 kb. Okay, so 132 kb you will get as the capacity of a track, which is innermost track. So this will be the answer for F portion, right? And then the next one, the next is if the disk is rotating at 3600 rpm. rpm means revolution per minute. So if we want to calculate per second, that is 1000 revolution per minute. Minute means 60 second. So that means 60 revolution per second. This is the speed. What is the data transfer rate? So what is the data transfer rate? In one revolution, one track will be crossed. In one revolution, one track will be crossed. And it is taking 60 revolution in 1 second. 60 revolution in 1 second it is taking, right? So when it is taking 60 revolution in 1 second, that means 1 second it is taking 60 revolution. 60, that means one revolution will be taken in 1 divided by 60 second. So that means 1 divided by 60 second it is being taken to travel one particular track. And on one track, the capacity we have already calculated. The track capacity we have calculated as I guess 256 or what. Okay, and that we need to divide by 60 and you will get the particular data transfer rate. So the data transfer rate will be equal to the capacity of the track, and the capacity of the track will be number of heads, capacity of one track, and then the number of rotation per second which you are taking. So if you try to calculate this, then let me go on. So we are trying to solve G portion, G. So let me solve it here. Okay. So in this, they are asking the data transfer rate, data transfer rate Now let's calculate the data transfer rate. We have already calculated number of rotations in 1 second. Number of rotation in 1 second is 60. That means for one rotation the time taken is 1 divided by 60. Okay. Now if you want to calculate the data transfer rate, the data transfer rate is equal to, you can say, the total data which you are transferring in that amount. So you need to find out number of heads, because each and every head will read some data. So whatever the number of heads, because each and every head will be circulating on a track. Okay, so number of heads, you need to multiply the capacity of track and number of rotation in a second. Number of rotations in a second. Okay, so the number of heads is equal to the number of surfaces, that is 16. Capacity of track we have calculated, like there are 256 sectors and each sector is of 512 bytes. So this is the capacity of track. And number of rotations in a second. So in a second, how many rotations? It is already given 16 rotations, because the speed is 3600 per minute. So per minute means 60 seconds. So per second it will be 60 rotations, which is written here, right? So data transfer rate will come like this. If you find out, it is 2 to the power 4, 2 to the power 8, 2 to the power 9 into 60 bytes, and it will come per second. So 4 or 8, it will be 2 to the power 21 into 60 bytes per second. That means 2 to the power 20 is mega. So 2 into 60 into 2 to the power 20, if you write bytes per second, that means 120 megabytes per second will be the data transfer rate. Okay. Now any other? Okay, I guess last portion is left. So the last is H. If the disk system has rotational speed is 3000 rpm, what is the average access time with a seek time of 11.5 millisecond? So let's solve the last one, that is H. In H, we need to calculate average access time. Access time of a disk. So how do we calculate the average access time? Average access time, the first thing we need to calculate the time taken in one rotation. The time taken to take one full rotation. So time taken to full, if we want to calculate the time taken for taking one rotation, it will be how much? So it is taking, the rotation speed is 3000 rpm. The meaning is in 1 minute it is taking 3000 revolution. That means in 60 seconds, it is taking 3000 revolution. That means in 1 second, it will be taking 50 revolution, 50 rotation, okay, in 1 second. So if there are 50 rotation in 1 second, that means in one rotation, time taken in one rotation is equal to 1 divided by 50 second. It means 1 divided by, that means it is 0.02 second. That means 0.02 second, that means it is 20 millisecond. Okay, so that means 20 millisecond is the time required for one full rotation. So in 20 millisecond, the complete track can be scanned by a reading writing head. That is the thing. Now we need to find out the average rotational delay. So if you find out the average rotational delay, how do you calculate the average rotational delay? The average rotational delay, it is, as I have already told you the formula of that, average rotational delay will be the half of the total time taken in one full rotation. So it is time taken in one rotation. So time taken in one rotation, it is 20 millisecond. So it will become 1 divided by 2 multiplied by 20 millisecond, which we have already calculated. That means it is 10 millisecond. So average rotational delay will be 10 millisecond, right? Now the average access time. So if you calculate average access time of the disk, the average access time of the disk is average seek time, average rotational delay, and if there is any factor, any other delay, then we can consider. So average seek time plus average rotational delay plus some overhead or some other overhead or factor delay. So if there is any other delay, maybe because of control unit or anything, then we can consider. So what is average seek time? Average seek time, if you look at the question, they have given you the average seek time. So let's look at here. Average seek time is 11.5 millisecond. So they have already given you average seek time. So it is 11.5 millisecond plus average rotational delay or latency we have calculated as 10 millisecond. So that we have already calculated, and no other delay is given. So other factors are not given. So it is 0, right? Now if you calculate this, it is 21.5 millisecond So 21.5 millisecond will be average access time of the disk. So with this example, I hope you are clear about how we can calculate the average access time, and there are different associated time with the disk like rotational latency, seek time, and number of other things. So I'm closing this session. Thank you everyone. See you in the next session.